talking more now about the coefficient of restitution, E. So basically, this is found experimentally. You know, take two things, measure them, bang them together, see what the coefficient of restitution is by measuring their velocities before and after. It depends very significantly on velocity, size, shape, just about anything you can think of. It's a very, very dependent little thing. So it's something that you're going to look up. It's not something that you're going to specifically calculate. So we've got a couple of different kinds of, or different specificities. So remember I said that E can go from 0 to 1. And 0 and 1 are more theoretical, but we'll just go ahead and define them. One type that you have is an elastic impact. And an elastic impact is when E is actually equal to 1. So specifically, you smush, and then you unsmush, and it comes out to 0. And this is the ideal, no energy is lost in the collision. And again, this is a theoretical thing, but practically impossible. So you have elastic, and then you have plastic. And probably when you were in physics, you called it inelastic. And your book calls it inelastic as well. It primarily says plastic. And that's when E equals 0. So basically the idea is that there's no rebounding. So they stick together. I think actually, looking up here, I think this needs to be equal, because if E is integral R over integral P, and then E is 1, then those have to be equal. So, alright, whatever. So they stick together. Nonetheless, it doesn't really matter because you're not going to specifically be looking at that. But anyway, the bodies will stick together when you have a plastic impact. So that would be an example whenever E equals 0. Now, to look at this, you need to kind of have a process for analysis. And remember earlier, like half an hour ago or whatever, I was talking about why it's important to draw these plane of contact and line of impact lines correctly. So it's kind of a generic, these guys are coming in like this, and this guy's coming in like however. We draw our line of impact, or, sorry, I'll try this again, plane of contact. And then perpendicular to that is our line of impact. Okay, remember doing that vaguely? Okay, so let me draw it straight up and down just to make it a little bit easier. Plane of impact, plane of contact, line of impact. Now, some velocity A, velocity B, 1 and 1. All right. So now this is going to be a little bit weird to think about, but basically the idea is, remember that conservation of momentum and everything that you've talked about, they're all vectors, right? So if you want to think about what this looks like, here's a way to think about it. Is basically, how do I say this? I think the best way to say it is that the coefficient of restitution, or little e, has to do with the velocity. Remember, I don't know if you remember whenever we actually defined E, it's way up here. What did we assume? Whoa, that was a really long time ago. We were doing a central impact, right? So that meant that they were all going in a line, hitting each other precisely in line. So we drew VA and VB like this, instead of drawing, VA like this and VB like this, right? We didn't draw them all cattywampus. We drew them straight, right in a line. Now, so what that really means, one way to think about it is that what we're really talking about, and what we were talking about up here, is the, if we pretended this was an XY axis, that we're talking about the X component of velocities of each of those at each of those particles or each of those points, not the y velocities. And so when we talk about, if you want to think about it that way, really what we're talking about is in this picture, the thing that deals with the elastic collision is this part. And your book doesn't call it x and y, but I'm going to call it x and y just to make it a little bit easier. Now, like I said, your book's not calling it x and y. Really what it's, if I was going to do this right, I'd say it's VA sub line of impact. That just is kind of hard to write. So I can name my axes any way I want. So whenever I work these problems, I just pretend my line of impact is my x and my plane of contact is the y. So whenever you're talking about the, what's it called, that thing, coefficient of restitution, what we're really looking at are the components that are along or parallel to the line of impact. Because think about it, I mean, it's kind of like the forces, you know, if I'm, if I've got something going along here, it's got its x component, or, you know, it's got its, say, x component of velocity, and it's got a y component of velocity. Now, the impact, it's only hitting on this side. Whoa, come back. It's only hitting on this side, so this shouldn't change at all, right? Because the force, if you want to think about it, is the force is perpendicular to that y component of velocity. So that y component of velocity shouldn't change at all because it's perfectly perpendicular to the force. So it's kind of like, you know, if I have a box sitting here on the ground and I sit here and like push on it really, really hard, that's not going to impact it. If it's, you know, yeah, think about it like that. If I've got a little box on a smooth, you know, plane, so like on an ice rink or something, and it's going zoop, and I sit there and I like bang on it, wow, 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 you know, it's not going to impact how that guy moves from left to right, right? Because it's a force that's perpendicular. Now, if it was falling in midair and I went pow, 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 then clearly it's going to go down even faster, in addition to, you know, gravity and all that stuff. But the idea is that the force, or the impulsive force, the impact, is perpendicular to that component of velocity. So that component of velocity is completely unchanged, which is kind of cool and maybe something you might have known intuitively, just never thought of. I don't know. But I think it's pretty neat. Anyway, I'm going to leave this here because it's a beautiful picture. So whenever you're looking to solve these problems, what you want to recognize is along the line of impact, and I'm calling that x just for simplicity. Along the line of impact, we do have conservation of momentum. So we have ma va1 plus mb vb1x vb1x equals ma va2x plus mavb2x. So the x components of the velocity are satisfied by conservation of momentum. And similarly, we can say that along the plane of contact, or y, that's met. But even with each individual, if we want to look at it, see, here we're looking at the system, I guess is what I'm trying to say. Sorry, my cat's bothering me. I'm trying to concentrate. So here we're looking at the entire system because forces are conserved within the system, but we couldn't do this. We couldn't separate it out, VA1x, and say, we could not say that this was equal to VA2x because there's this inelastic, you know, collision or restitution force. There's going to be some force acting on it. So since we're looking at, if we were looking at the particle, we'd have to include this, and we can't because we don't know what it is. So we have to look at the entire system as a whole in order to do that. So the way that we include that information about the restitution and the smushing is by actually using our coefficient of restitution. So bx, or bx2 minus VAX2 over VAX1, or minus VB1. Oh, I was putting the numbers first, wasn't I? VB2X, VAX, x and 1x. So we're able to keep this information here in the system, but we have to do it this way because the forces, the impact is happening along that x-axis or along that line of impact axis. Now along the plane of contact in the uppy-downy direction, we can look at each particle because there's no forces acting in the up and down direction. We could go ahead and write it out. Some of the forces dt. But this is actually 0 because there are no forces in the up-down. And that's because that's how we defined it. We defined plane of contact as being perpendicular to the impact. So since plane of contact is perpendicular to the impact only happens up here at the system level. So, I mean, up here in the xy, that's why we have to look at it as the system level. Because if we didn't, we'd have to include the FDTs, and then we wouldn't know what they are. So the way that we take care of that is we involve this equation here. So in this case, you would probably know these two, and you'd be asked to find these two. So you still have two unknowns and two equations, so it's still something that you can solve. It's an interesting thing to me, I guess. So I keep coming back down to here. So that's why your line of impact. Again, I'm just trying to emphasize why at the system level you don't include that, because I mean you don't include those integrals because you're looking at the whole system. You have conservation of momentum at the system level, and then here is where you relate the velocities based on those restitution forces that are happening internally. Now here on the other side, along the plane of contact, we can actually look at the particle level because that particular term actually goes to 0. So if you take a look here at what's going on, and this is what I just explained verbally, but now we'll prove it mathematically, that if that's 0 and I can cancel out my masses because they're the same on both sides, then that means that my y velocity is the same before the impact as after. So whenever you're solving these problems, you kind of want to separate things out from line of impact and plane of contact, which is really separating out into your x and y, recognizing anything that's happening perpendicular to the force that doesn't change. Velocity is not going to change because it's perpendicular to the force. Things that are in the line of the force are going to change, and we're going to have to take advantage of the coefficient of restitution in order to take care of that. So that's really, really important. One more thing I want to make sure that I alert you to as you're solving these problems is that you need to make sure you use all your tools. So again, don't forget about this. We'll have F equals ma, right? So you got your sum of your forces is going to be equal to ma. So you still have the possibility of using this. You also have conservation of energy. And this could be very useful. There's an example out of the book that that we've got, you know, where you've got this spring and you don't know time and you don't know S, so you're trying to do this, you know, and you can't figure it out. And you're like, well, what do I do? What do I do? Well, you know the conservation of energy of a spring. So, you know, we can use conservation of energy. If you're trying to do conservation of momentum and you're like, oh my gosh, this isn't working, try conservation of energy. You might, I mean, that still uses velocities. It uses, you know, K's. It uses forces. It's a good little thing to have. So make sure that you don't forget that you have that. And then, of course, now we've added this additional tool, which is conservation of momentum, which we now have, and it's something we didn't have before. So make sure that you remember that you can use all of these, and we'll continue to make these tools more sophisticated and more useful as we go along. But again, just don't forget that you have all these available, use them, and if one doesn't work, try going with another one.